So, hello and welcome back to my exploit development playlist. In this video, we will be solving the challenge Fluff from Emporium. And the concept here is very similar to the Write 4 challenge, although we might struggle to find several gadgets that we can use. So, okay, let's get the binary again and take a look. So we again have a binary and a library. Let's take a look at the security stuff with checksec and same stuff as usual. So let's open it up in GDB straight away, find our offset, and I'm placing my bets on 40. Let's see what we get. And looks like we are at 40 again, so we can note that down. So let's open up another terminal, and I think we can close this here. Maybe there's some gadgets are available at questionable gadgets, and we need to print a file. And also we know that this challenge is probably painful, but other than that, I don't think we need that. So let's go to here and open our pwn script. Again, our shebang again. And we can, of course, set the context binary. That's our binary. Then we can also set the context terminal, which would be kitty. And then we can already define offset, which 40 again. So we can define heading of 40 A's again. And then let's see how we can get started here. And there should be questionable gadgets in here. So let's take a look. There's a lot here. So maybe let's quit out of here and open this really quickly in Redare. And there's useful function. So let's maybe take a look there. And there's our call to print file again, and there's a non-existent string. So we can already specify our call to that call to the PLT entry to the print file, but that should work just fine. Otherwise, we could probably jump here directly, but yeah, I think that's fine. We can just jump here, then into this call, and then we don't really care about the return, so that's fine. After that, let's take a look at where we can write. And we can still read and write to the data section, so that's enough for our flag. So let's just take this like that. And then we can plan out our payload. We would like to write into our data section, but first of all, let's go step by step. Just need our padding, so we can start to write return addresses. Then there will be some stuff. Then we will need to load our argument for the print file into RDI. So we would need to have some pop RDI, and we already know where we will have our address, and that is at the data section. Then after that, we can call our print file like so. And of course, pop RDI is not defined. And then we of course need to send our payload again, and that can be done with process again. It already knows the path, and then we just send line after that caret again. I think we needed to specify this as byte string, then payload, and then we can switch into interactive mode. And so far so good. Then here we need to somehow load flag.txt into data section. And yeah, that's pretty much what we need to do. We can define some gadgets here. And we know the first gadget that we want is a pop RDI. Let's see if we can find one. Here are our questionable gadgets. We can already see a store of a single byte from AL to whatever RDI points to. So that is probably how we can write to the data section. I don't know about this. And we need to find, and there's exactly one. So let's copy that and paste it into here. That's not the right one. Still not the right one. I'll paste that into here. So that is our pop RDI. And then we need to figure out how we can load flag.txt into the data section. And it looks like we need to write single bytes using this here. So we need to get the address into RDI and the value into AL. So we can at least write the gadgets down that we have. So we have RDI, and that is that. We will probably also need this. Not sure from where on. Can probably use this. So we can also utilize our pop RDI and the data section to get the data section into RDI to start out with. And then we can define our flag string like so. And then we somehow need to write it. And for that we need to get the value into AL. I think I need to look up how x_b works exactly. So let's see. Make this a little bit bigger. Table lookup translation. I got something along these lines, but I can't remember what exactly it does. x_let e basically then transforms an offset that we provide in AL into a concrete L value from a table that we provide in RBX, and it looks up in that table by adding that offset that we provide in AL, and then uses that value that it finds at the offset of where we provide it in AL and loads that into AL again. So I think we can use that right before here to load into AL as we wanted, but before that we then need to prepare AL and also RBX, and to do that So finally, after some debugging and frustration off screen, I finally have a working exploit, and as you can see, I've already written it down and prepared it. So let's just go through it. This challenge was really hard compared to the last ones. So first of all, I did some mistakes here. Of course, we don't call this as a function. We just assign it like this. Nothing changed here. And yeah, we also have another useful gadget that I needed to look up. This is a bitfield extract command that we have in here. And that bitfield extract in our case basically copies from RCX into RBX. Okay, then here we start out our payload and we fill out our buffer with the padding that we've calculated here. That's just for the A's again. And after that, we populate RDI with our data section offset. Then ignore this for now. We loop over our flag txt and we use enumerate to get the index and also the character at each location. And then I needed to have the character address somewhere in the program, and I didn't find any useful gadgets to get them off the stack. So I just searched for them for the characters in the program itself. And we can do that with the elf search command that returns a generator. So we need to call the next function on it. And then here's some information text for debugging purposes. Then here we have our bit exchange stuff where we provide the length in RDI. I just provided 40 characters just randomly, and then the starting index, which is just 0. And now here it gets a little bit tricky. We prepare the RBX here for our next command, and we always needed to adjust for this arbitrary add. This can be found here at RCX. We copy from RCX to RBX, and we needed to adjust the position here for this arbitrary add. And then also there is a value already in AL that we can't zero out. There is no X or RAX gadget anywhere. I thought there would be one, but we need to take that into account here. So we find the initial value that RAX holds, and before it reaches this command. And I just stepped through it in GDB and found it was 0xb. And after this command, this basically loads whatever we have in RBX plus AL into AL. So that's wrong, like this. So what we need to do here is to account for the AL value that's already in here in our RBX calculation here. And yeah, this X let B basically just indexes RBX by AL and then looks up the value that it finds there and puts it back into AL. And as you can see, then AL holds the old value of the character. So we need to take that into account here. So for any following call here, we need to subtract the last value that we put in here. So this effectively is zeroed out again. Yes, so much for that. And then we can finally do the string store. And that's really simple then. And we move that into our data section. And then finally, after all that is prepared, then we have basically our flag.txt loaded into our data section. And we can get the data section back into RDI here. I think that wouldn't be necessary, but yeah, just to be safe, we prepare this again, and then we can call the print file. And to show you that it actually works, let's call the fluff exploit script here. And as you can see, we've solved this challenge. This one was really tough. Let's see if we can do the next one.